Okay, so we are in the last section for Chapter 1. This is the last bit of theory that you're responsible for your first test. So what we want to do is we want to formalize the definition of a vertical asymptote. And we want to do a little bit of pre-calculus by just finding vertical asymptotes. But let me read the following definition. So, if your function approaches infinity or negative infinity, as x approaches some number we'll call c, right? So, from the right or left. So let's make sure we understand that. So if your function approaches infinity, so notice that in this case, our function is approaching infinity or negative infinity. And that is happening as x approaches some value c from the left or right. So that's what the first part means. So if that's the case, then the line x equals c is a vertical asymptote of the graph f. So this dotted line that you're seeing here is the vertical asymptote for that function. Now, it should go without saying that a vertical asymptote is a graph. So so it's very important that when you tell me, if I ask you what's the vertical asymptote, if there is one, you should begin with x equals, right? So for example, if x equals 3, well, that's a line that I can draw. That's a vertical line that runs through every y value with x remaining 3. If there's a vertical asymptote at x equals 3 and you just say 3, well, I don't know what that means. Well, truth be told, I do know what that means, but we're being a little bit too sloppy, right? A vertical asymptote is a line. It is a vertical line that is a graph, and you should have a variable, so x equals. Make sure you always answer the questions x equals. All right. So starting with example 1, it says determine some infinite limits, right? So that's the topic, right? Infinite limits, meaning your limits are approaching infinity. So we're going to take the following function, 1 over x minus 1 squared, and we want to approach it from the left of 1, and we want to approach it from the right of 1. Okay, so the whiteout that you're seeing, again, because I don't have all my materials that I would have if this were on campus lectures, so I just had to white out the answers so that we could continue. So let's start. Let's find when x equals 1. So here's where x is equal to 1. So I tell you what, let me use a different color. All right, so right here, this is when x is equal to 1. Okay, and what we want to do is, let's see what our function does as you approach 1 from the left. So if you're going to approach 1 from the left side, that would be from all the values smaller than 1. So what is your graph doing? What is the limit? Well, notice that your graph, as you get closer and closer to 1 from the left, your graph is just moving towards positive infinity. So the answer is infinity. And notice it's the same thing if you were to approach 1 from the right side. So now we would be approaching 1 from numbers larger than 1, but your graph is still moving upwards to positive infinity. Okay, so different function. Now it's negative 1 over x minus 1. And we want to, again, discuss the limit as x approaches 1 from the left and as x approaches 1 from the right. So to kind of speed things up, so here is the graph. So here you're approaching 1 from the left side. And notice that your graph is moving towards positive infinity. So the limit as x approaches 1 from the left is going to be positive infinity. But notice if you approach 1 from the right side, look at where your graph is going. Your graph is going down to negative infinity. So the limit as x approaches 1 from the right is negative infinity. Okay, so finding vertical asymptotes. So let me make a statement, and maybe I can use the previous page to make the statement. So it appears that, so notice that when x is 1, if you plug 1 into the denominator, you would be dividing by 0. Same thing here. If you plug 1 into the denominator, you would be dividing by 0. So now let me make a statement. If there is a vertical asymptote in the graph, right? So if one of these exists, then it will occur when you are dividing by 0. Okay, so this vertical asymptote occurs when x is equal to 1. All right? So I want to make sure you understand what I said and what I did not say, okay? Because the converse of that statement is not true. I said that if a vertical asymptote exists, it exists at a point where you're trying to divide by 0, okay? What I did not say is that if you're trying to divide by 0, then you have a vertical asymptote. And let's make sure you understand why. Not both of those statements are true. It's not biconditional. So let's start with finding some vertical asymptotes. So we'll start with the graph, or this time we won't look at the graphs themselves, right? Because that would be cheating. Let's just look at the function. 1 over 2 times x plus 1. Okay, can you and I agree that x obviously cannot equal negative 1, right? If you allow x to equal negative 1, then you would be dividing by 0. So that's true. Now here's what you don't know. So division by 0, so let me write c divided by 0. Division by 0 can occur, geometrically, can occur at a vertical asymptote. Now I'm just going to put VA since I don't have a lot of space. So it can occur, division by 0 can occur geometrically at a vertical asymptote or a hole in the graph. So if your graph has a hole in it, then that would cause division by 0. If your graph has a vertical asymptote, then that would cause division by 0. So what we don't know right now is when x equals negative 1, we know it's causing you to divide by 0, but what we don't know is that a vertical asymptote or is that a hole in the graph? Let me just state that if there is a hole in the graph, then you should have like factors that can cancel. Let me show you exactly what I mean by coming back to A and going to B. So take, for example, B. So right from the beginning, you and I can make the statement that x cannot equal positive 1 or negative 1. Either one would cause division by 0. But now, again, what we don't know is, does that mean there's 2 vertical asymptotes or 2 holes in the graph, or 1 vertical asymptote and 1 hole? So how do we find out? So what I'm going to do is I'm going to factor this function, okay? And what I'm going to tell you is if there is something, a like factor, something that can cancel out, then that would represent a hole in the graph. If there is nothing to cancel, then that would represent vertical asymptotes. So notice that in this case, there is no way to factor the numerator. I just have to leave it as x squared plus 1. But I can factor the denominator. That would be x minus 1 times x plus 1. Okay, so let me be really informal, but straight to the point. So I have an x minus 1 in the denominator, and I have an x plus 1 in the denominator. If I have an x minus 1 in the numerator, or an x plus 1 in the numerator, that would be the hole in the graph. I'll say that again. If I had, which I don't, but let's just assume for a second, let's assume that I had an x minus 1 in the numerator. So if I did, then this x minus 1 would cancel this x minus 1. And what I'm telling you is that would be where your hole is located. But if I don't have anything to cancel, which I don't, then both of these are vertical asymptotes. So finding the vertical asymptotes. So the vertical asymptotes exist at x equals -1 and x is equal to +1. Notice I did not just write a -1 and a +1. Okay, because I'm making a statement about an equation, right? About a graph, and that graph is just a vertical line. So let's go back to part A. So we already know that x cannot equal -1. Is there anything to cancel here? Is there any other x plus 1s? Well, no, there's no other. So I know that there's no holes in the graph. So a vertical asymptote exists for part A when x is equal to -1. Okay, so part C, all we need is to understand that cotangent is just like tangent, is a fraction. So cotangent is the multiplicative inverse, or I should say the reciprocal, I'm sorry, of tangent. So tangent is sine over cosine, then cotangent would be cosine of x over sine of x. Okay, so if we want to find the vertical asymptotes for cotangent, then we would want to know what angles would cause sine of x to equal 0, right? Because that would be division by 0. Now the good news is there are no holes in the graph. So let's just assume that we're only interested from 0 to, let's just do 2 pi. Okay, we won't do the entire cotangent curve. So from 0 to 2 pi. All right, well, let's think about it. So clearly sine of 0 equals 0. So for sure, x cannot equal 0. What else? Well, sine of pi is also 0. So that would cause division by 0. So x cannot equal 0 and it cannot equal pi. So if you wanted just from 0 to 2 pi, then your vertical asymptotes would be x equals 0 and x equals pi. Those would be your two vertical asymptotes. So for those, if you wanted all the vertical asymptotes for this problem, then it would be x is equal to n pi, where again n is just an integer. Okay, and anytime there's any multiple of pi, you're going to be dividing by 0. Those are all vertical asymptotes. So here's your vertical asymptotes. Okay, so let me show you one more time. This is probably the best problem that we've done so far, because I'll just go ahead and tell you there's going to be one of these. There's going to be a hole in the graph and a vertical asymptote. So now notice that your task is to find the vertical asymptotes. Your task is not to find the holes. So, all right, well, let's take a look at the denominator, x squared minus 4. And the question that we're asking ourselves is what x values would cause x squared minus 40 equals 0. Now, some of you can do that in your head very quickly. The whole point of why you spent so much time factoring in, say, middle school, high school, is so you can take advantage of this zero product principle. The idea that if A times B equals 0, that's true if A equals 0 or if or B equals 0 or both, right? So the inclusive or. Now, so it's, for some, this might be hard to take a guess at what squared minus 4 equals 0. For many of you know that you can do that in your head. But you don't have to. If you factor the denominator, which is what we're about to do, well, that's just the difference of two squares. So that would be x plus 2 times x minus 2. And now the idea is, think I have two factors, right? If I can get this first factor to equal 0, then it doesn't matter what the other factor is, because anything times 0 is 0. Likewise, if I can get this factor to equal 0, then who cares what x plus 2 is, because anything times 0 is 0. So now we can just use inspection. So clearly, if x is equal to negative 2, that would cause the first factor to equal 0, meaning the whole left side of the equation would equal 0. Likewise, if x were to equal positive 2, then that factor would equal 0, meaning the entire left side of the equation would equal 0. So what we know as of right now is that x obviously cannot equal negative 2 or positive 2. What we don't know is, does that mean there's two vertical asymptotes, two holes, or one of each? So that's the game. So now, the good news is, to finish this up, let's go back and rewrite the original problem. But let's factor both the numerator and the denominator. So we've already factored the denominator. So that's x plus 2 times x minus 2. Now all we have to do is factor the numerator. So I won't waste your time reteaching you to factor, but that if you factor that numerator, it would be x plus 4 times x minus 2. Okay. So it's at this stage you're able to spot which of these, right? Because you have two choices. Which one is the vertical asymptote and which one's the whole? Are you ready? Okay, let's see if there's anything that cancels. All right, do you agree with me that the x minus 2 factors cancel out? Okay, well, what you just canceled was the hole in the graph. So what's left? So let me write it. So once we have x plus 4 times x minus 2 over x plus 2 times x minus 2, as soon as these factors cancel, that is, by definition, the hole in the graph. Okay? I'll come back and just give you a broader picture of why that is the case. But so let's write what's left. Well, what's left is the x plus 4 over x plus 2. Okay, so that would mean that this, whatever causes your denominator to be 0 here, this is the vertical asymptote. All right, so what would cause what we have left, the fraction, what would cause there to be division by 0? Well, that would occur, don't you agree, that if x were to equal negative 2. So if x equals negative 2, you have a vertical asymptote. If x equals positive 2, that would be the hole in the graph. All right, so since we were only asked to find the vertical asymptotes, the answer is simply x equals negative 2. That's the vertical asymptote, and you can see it from the graph. So here's the vertical asymptote. What doesn't show up very well is the hole that's in the graph when x equals positive 2. So positive 2, there would be a hole here. Okay. All right, so that's how we find vertical asymptotes. That's by the way, just to kind of take you a little bit farther, remember that limits can exist when there's holes in the graphs, right? You can approach the same number from both sides. If you were to plug 2 into this function, you would get 0 over 0. If you plugged a negative 2 into this function, you would get a constant divided by 0. So just for a little bit more understanding, that's why we can think of it as canceling out the hole in the graph. All right. I hope that, I'm getting a little bit tired, so hopefully that made sense. Hopefully I said everything correctly. All right, so let me kind of, the last topic for this first chapter is what we call limits at infinity. So there's a difference between saying infinite limits and limits at infinity. So when the at infinity part means that you're approaching infinity. Oh, I should say, my sincere apologies. Infinite limits is what we just did, limits at infinity, right? I believe. So now we're going to be doing infinite limits. I told you I'm getting tired. By the way, I don't edit any of my videos, so no matter what I say, it is recorded forever. So infinite limits. So this is going to be the idea here. So let me start with just a quick observation. I think this will make much more sense in just a second. So can you agree with me that let's just say that, well, let's say that you have $2 in your pocket. Now, if you are kind enough to share your $2 with 2 people, will you agree with me that each get $1? Okay, well, what if your generosity knew no bounds? What if you decided to take your $2 and share it with 100 people, or 1,000 people, or 1,000,000 people? Well, don't you agree that the more people that you share your $2 with, the less each person gets, right? But what about if you were so generous, you were to share your $2 with an infinite amount of people, 2 over infinity? Will you agree with me that in that case, nobody would get anything? So if you share your $2 with an infinite amount of people, nobody gets anything. That's the idea behind this. So when you take the limit as x approaches infinity of a constant, when it ends up being a constant over infinity or negative infinity, doesn't matter, it equals 0. So 3 over infinity is 0, 4 over infinity is 0, and so forth. In fact, this little trick, when we just study horizontal asymptotes, will be much more meaningful. Okay, well, now let's think about if you, instead of approaching infinity, right? Instead of letting your x go to infinity, what if you let x go to 0? Okay, well, the limit as x approaches 0 of 2 over x is going to be different if you're approaching it from the left side or the right side. But what we know is it should be going to either infinity or negative infinity. So let's go back to our $2 example. So if your denominator is really small, right, 2 over a tiny number like 2 over 10 cents or 2 over or even smaller number, when your denominator x is small, then f of x would be large. When your denominator is large, then f of x would be small. So let's try to use some of these intuitive ways of thinking about this to our advantage here. So let's take a look at, we'll do it geometrically. What happens as you approach 0 from the right? So this is the graph here. This is the graph of 2 over x. All right, and now let's start by approaching 0 from the right side. Okay, so I would be dividing by a very small but a positive number, right? Because anything to the right of 0 is a positive number. So I would, as you get closer to 0, I'm dividing by smaller and smaller and smaller numbers, but they're positive numbers. So if you divide a number, so 2 divided by a really small number should go to infinity, and since that's a positive number, it should be going to positive infinity. So positive infinity. But now, if I approach 0 from the left side, well, my number is still really, really small. So I know it's going to infinity or negative infinity. But it's a really small negative number, right? So anything to the left of 0 is negative. So this ends up being 2 over a negative number, a very, very small negative number. So that's why you can see that your graph is approaching negative infinity. Okay, so what we want to do is we want to see if we can determine some of these infinite limits. So let's take a look at x squared minus 3x over x minus 1, okay? And we're going to see what happens as you approach 1 from the left and from the right. Okay, so I have provided the graph for you. And what I think you might, it's up to you, but you might find it beneficial if you go ahead and factor that numerator. So it would be x times x minus 3 over x minus 1. Now again, I think in terms of geometry. So the way I would view this, so first let me find exactly what number it is that's of interest. So this is, right here is when x equals 1. And now let's start to approach 1. We want to approach it from the left side and from the right side. All right, so let's start with from the left side. So here is, so hopefully you're starting to anticipate these answers. So as you get closer and closer to 1 from the left, your graph is going towards positive infinity. As you get closer and closer to 1 from the right, your graph is going to negative infinity. So my answers here are positive infinity and negative infinity. Okay, now if you assume that you might have trouble producing a graph, or at least a quality graph, another trick that you could try is, let's go back to 1, pick a value that's close to 1 but smaller than 1. Like try picking 0.99. Don't you agree with me that 99 cents is smaller than 1? So you could try plugging 0.99 in for x and see if you get, obviously you're not going to get infinity, right? But see if you get a negative number or a positive number. A really small number or a really large number. Same thing over here. You could just pick a number slightly larger than 1, so like say maybe 1.01, and plug it in for x. And again, see if you're getting a negative number or a positive number. So that's one way of thinking about this. Okay. We're almost done. I do see a mistake happen enough that I think I should point it out to you. So take, for example, this guy right here in factored form. I can't count how many times I've seen students cancel the x values, right? It's like it's you see an x here, you see an x here, you just want to get your pencil out and start canceling them, right? But it's important for you to understand that we do not let me state it formally. You're allowed to cancel factors, but you cannot cancel terms. I'll make sure you understand what I'm saying here. Notice the difference between this. Okay, in the first example, there's a 3 here and a 3 here that you may want to cancel. In the second example, there's a 3 here and a 3 here that you may want to cancel. One of these is perfectly fine. The other is not. So let's imagine a student, 2 students, okay? One decides to, let's start with the first example. One decides to cancel the 3's first and then multiply. So in that case, they would have 3 times 2 over 3, whereas the second student just multiplies and then reduces. So let's do, the first student decides to cancel the 3's, so that would be, they would be left with 2 over 1, or just 2. The second student decides to multiply 3 times 2, which is 6, and then divide the 6 by 3, which is also 2. So notice how whether you cancel the 3's first or multiply first, you still get the same answer. Let's imagine the same students here. The first one decides to cancel the 3's. So, and then the other one decides to add. So the first student cancels the 3's. They're left with 2 over 1, or just 2. The second student decides to add. So 3 plus 2 is 5, and 3 plus 1 is 4. Now notice that the first student got 2 as an answer, and the second student got 5/4 as an answer. Well, in mathematics, you can both be wrong, but you can't both be right. So one of these students, or both, has to have made a mistake, and the idea is it's the first student. This cannot work. So let me state what I said a second ago. These are factors. You're allowed to cancel factors, but you are not, these are terms separated by plus or minus. You cannot cancel terms. So up here, can you cancel your x's? Absolutely not. This is a factor, x times x minus 3, but this is a term, x minus 1, so you cannot cancel. All right. So what I want to do is, because for sometimes the infinite limits section can be slightly difficult, but I really think it's for those that are overthinking it. Let's start with some properties, right? Some basic properties. So what we're going to do is we're going to let the limit we have x is approaching c, okay? And we have a function f and a function g. One of those is equal to an infinity. The other is equal to some real number. So when they say f plus g or f minus g, that just means infinity plus a real number, or infinity minus a real number. The idea is, will you agree with me that, let's make it simple. Let's say infinity plus 2 is still infinity. Okay? You don't add 2 to infinity. It's infinity is not a number that you can manipulate like that. Likewise, if you have f times g, well, this, in our case, this would be infinity times 2. Well, that's still infinity. Okay, that's if you're dealing with a positive number L. So infinity times positive 2. So what if it was infinity times negative 2? Well, negatives times positives, still negatives. So that would be a negative infinity. And I've already mentioned this one. So in this case, you would have g is 2, and let's say f is infinity, just like the $2 bill example I was telling you about, that chopping up $2 an infinite amount of ways is equal to 0. Okay. So what does that mean for us? So in this, to kind of wrap this up, so in these particular problems here, we want to take the limit as x approaches 0, and we can do it term by term. Well, let's start with the limit as x approaches 0 of 1. Well, that's just going to be equal to 1, right? The limit has no bearing on a constant. Plus, well, what about the limit as, let's go ahead and make this from, we'll make it from the right. I think I erred there. So the limit as x approaches 0 from the right of 1 is still 1, has no effect. The limit has no effect on a constant. But what about if we approach 0 from, limit as x approaches 0 from the right? Well, again, this is your graph. This is you approaching 0 from the right side, and all I want to know is, am I going to infinity or negative infinity? Well, I'm going to positive infinity. So we end up with the statement 1 plus infinity, which I just want you to answer as infinity. Try another one. So now we're taking, let's see here. So we got the limit as x approaches 1 from the left side, and the function is x squared plus 1 over cotangent of pi times x. All right, so here's my graph. Okay, so there's no separation here. This is all just one term. But the way we're going to do this is, let's start by plugging in, well, you can think of it as, we can start with the numerator, right? So what happens as you approach, well, you can do two ways. You can look at if you have access to a graph, it's, right, this is much more beautiful if you think about it as, so let's say, so here's 1. If you want to approach 1 from the left side, notice how your graph is going up to positive infinity. So I know, just geometrically, I know that my answer, let me make sure I made sense of all that. Well, by the way, it's 2 in the morning here, so let me make sure I understand what I just said. And did I even graph it correctly? So x squared plus 1 over cotangent of pi x. Okay, well, let's start with the numerator. So if you plug 1 in for x squared plus 1, that would just be 2. And now let's approach 1. Oh, my sincere apologies. It definitely is getting late. So if we think about, so this is 1 right here. That's where I went wrong. Okay, so if I'm approaching 1 from the left, right, you can see that from the left side of 1, your graph is going to negative infinity. Not that it really matters, because when you take your constant of 2 and chop it up in infinite amount of ways, whether it's negative or positive, it's going to 0. So, last one. So we have, we're dealing with 3 cotangent of x, and we want to take the limit as x approaches 0 from the right. Okay. So here's the graph of 3 cotangent of x, and the number we're interested in what's happening here at 0, and we're interested in what's happening as you approach 0 from the right side of it. So geometrically, I can already see that this should be going to positive infinity. just like up here, you can see that it's, yeah, you can, just like up here, you can see how it's going to 0 here. Now, but let me see if I can justify that a little bit more. So you can think about separating. You can think about taking the limit with x going to 0 of 3 separated from the limit with x going to 0 from the right of cotangent. So in this case, let's start with the constant. Well, we know that the limit has no bearing on the constant, so we're going to get 3. But the next question is, well, what about the as x approaches 0 from the right side of cotangent? Well, again, if you have access to a quality graph, you could look at the geometry of it. If you don't have access to a quality graph, you could try choosing numbers slightly larger than 0. But the real question is, am I going to infinity or negative infinity? And what you would see is that you're going to positive infinity. So we end up with the statement 3 times infinity or infinity. Okay, so I hope that was okay. And if not, again, feel free to reach out to me. That should wrap up what you need to know for your test. You guys take care and stay safe.